Hi, Dr. Ryan. This is our presentation over the valve cover problem. I'm Jack, and my partner here is Jacob. And for this problem, first, we had to consider a given shaft radius and the connecting rod length, and how far to the left and right the valve cover would move. And second, our other consideration was how important it was to estimate stress on certain parts. This means we had to find the cover's extreme positions, its max velocity, and max acceleration. From there, we can make observations on the phenomenon itself. And now we can move to our positions and setting the problem up.
So what we know, or what we were given about the problem, was this. The shaft QP is 4 inches long. The radius of the shaft is 1 inch. The shaft turns counterclockwise at 60 RPM or 1 RPS. We have our Q position of x equals the cosine of KT and y equals the sine of KT, but we need to solve for P. To get P's positions, we first had to find the position of Q. To do this, we estimated that K was equal to 2 pi since the shaft moved at 1 revolution per second, and assumed that T equaled 1 second, which would make Q at 1, 0. We then set up a triangle with the rod's hypotenuse of 4 and used the Pythagorean theorem to get this equation. The position of P is equal to the square root of 16 minus 3 plus sine 2 pi times t squared plus cosine of 2 pi t. Using this, we got the initial position to be at x equals 3.65 inches. Plugging this equation into Excel, we found our extreme positions. The left is at negative 0.364 inches, or t equals 4.2 seconds, and the right is 4.42 inches, or t equals 7.8 seconds.
After finding our initial positions, we could then move to finding the max velocity and the times at which this occurs. So, for the absolute value of the valve cover's max positive velocity, we found that to be about 12.20 inches per second. And we can see that this occurs around t of 6.3 seconds, and again at various other times, such as t equals 14.3 seconds and t equals 22.3 seconds, or about every 8 seconds. Then the negative velocity is about 12.23 inches per second, and this occurs around t of 2.1 seconds, t of 10.1 seconds, and t of 18.1 seconds, which also follows a very similar 8 seconds pattern. The negative velocity, if taken the absolute value, is the higher velocity, so our max velocity is around that 12.23 inches per second. And if you look to the right, you can see the pattern following a graph that kind of has this neat looking pattern that's a squiggly. Then you can see the highlighted T's of those max velocities.
Moving out of velocity into acceleration, we were able to find the acceleration by taking the change in time of the velocity. And what was interesting to note is that the initial acceleration of P is negative as well as the initial velocity. The max acceleration, though, is 115.08 inches per second squared and occurs at t equals 4.1 seconds, and again later at various times, such as at t equals 12.1 and 20.1 seconds. In other words, it happens about every 8 seconds, just like with the velocity.
So, velocity as p passes through the y-axis. As you can see from the extreme positions as well as a few other spots following a pattern, p does pass through the y-axis a few times, but just barely. This occurs at the extreme, which is negative 0.364 inches, which is at t of 4.2 seconds, and also a negative 0.229 inches at t equals 3.2 seconds. At the same time, for the extreme position, the velocity changes from negative to positive, and this occurs around t equals 4.1 to 4.2 seconds. This change of velocity likely means that the velocity as it passes through the y-axis is at 0 inches per second, because it is not moving at all at the instant it is passing through the y-axis. Another result of this phenomenon is seen within the acceleration at t equals 4.1 seconds to 4.2 seconds. we see a dramatic decrease in acceleration for 115.08 inches per second squared to negative 26.17 inches per second squared. This is interesting as the acceleration jumps from a super high number to a large negative number. And you can see these little images to the right of how these groupings are at the exact same times and how we can have this observable phenomenon. It's also interesting.
Some interesting features that we found in P's motion were about how it mostly stays in the fourth quadrant, but it briefly goes into the third, although just by a hair, then jumps back to the fourth before going back to the third again, only to go back to the fourth for a much longer time. This back and forth motion takes about 1 second to complete, and then happens again about 7 seconds later, for a total of 8 seconds, which is about how long it took the max velocity and acceleration to happen again. Speaking of the velocity and acceleration, they also strike us as a bit odd here. For one, the velocity almost instantaneously shifts from negative to positive whenever the valve cover passes through the y-axis. This, in turn, causes the acceleration to shoot up sky high, only to fall back down again instantly. This is a great example, in my eyes, of how position, velocity, and acceleration are all connected.
Now, what would happen if we reverse the shaft's rotation to turn clockwise? Well, if we reverse the rotation to spin clockwise, everything would typically, just about stay the same, except it would be flipped across that y-axis. This would mean that the max left position would be about negative 4.42 inches at t of 7.8 seconds still, and the max right position would then be at 0.364 inches, or still at t of 4.2 seconds. The absolute values of the velocity and acceleration would still be around those initial values that we found of 12.20 inches per second and 115.08 inches per second squared, respectively, because the absolute value will always be positive. The velocity as p passes through the y-axis would still also be 0 inches per second, as it is still coming to a stop and quickly changing from negative to positive, and vice versa.
All in all, the valve cover design is an interesting problem. The structure presents a limited movement upon the cover. Moreover, at face value, it seems the valve cover would not go past 0 on the y-axis. As shown by the work, though, it clearly does. Because of the circular rotation's pull on the cover, it forces it to stop around the midpoint, but the force generated by the revolutions forces the cover to extend a bit past the y-axis. The effect this small part has is huge, as it greatly affects the velocity and acceleration of the cover. It was a difficult problem to start working on. However, once the work accumulated and the graphs were drawn, the movement of the cover was very interesting.
And that's it. Thank you for listening, Dr. Ryan.
Thank you.